In the grand narrative of scientific discovery, we encounter a figure of unparalleled vision, Freeman Dyson, the maker of patterns. This slide introduces a man whose intellectual reach spanned the entire breadth of reality. From the hidden intricacies of the subatomic world to the majestic sweep of the cosmos, Dyson spent his life identifying the fundamental structures that govern our existence. Framed by the very mathematical formulas he navigated with ease and anchored by the seal of the National Academy of Sciences, we prepare to explore the legacy of a mind that found harmony in the infinitesimal and the infinite alike. Join us as we journey through the life of a thinker who truly mapped everything in between. In the landscape of intellectual pursuit, Freeman Dyson categorized genius into two distinct roles: birds and frogs. The bird, exemplified by Einstein and Schwinger, surveys broad vistas from the air, seeking grand, unifying theories of everything. Conversely, the frog, Dyson's own avatar, thrives in the mud, focusing on the intricate details of specific flowers. Alongside Richard Feynman, these frogs solve specific, complex problems wherever they are found. While the bird seeks the horizon, the frog embraces the immediate challenge. The frog's advantage lies in a radical openness, the willingness to say yes to everything. It is through this granular focus that the frog discovers the profound patterns hidden in the specific details of our reality. Infinite in all directions, maps Freeman Dyson's intellectual journey across the vast dimensions of existence. It begins at the subatomic scale of 10 to the minus 15 meters, where his work unified quantum electrodynamics. Moving to the terrestrial scale, the focus shifts to his advocacy for safe nuclear reactors and global disarmament. His vision then ascends to the cosmic realm, exploring the revolutionary potential of Project Orion and the energy-harvesting Dyson swarm. Finally, the journey reaches for the infinite, the abstract domain of the human soul, philosophy, and futurism. This trajectory captures a life dedicated to following curiosity from the infinitesimal to the edges of the universe, bridging mathematical precision with the profound mysteries of our place in the cosmos. In exploring the architect of additive number theory, we see a legacy built on three pillars. First, the catalyst, Dyson's mentorship at Trinity College under G.H. Hardy. This led to the artifact, Dyson's transform. Developed for his proof of man's theorem, this technique was later used to show that every even integer is a sum of at most 6 primes. Finally, we examine the philosophy of his work. Dyson maintained that a mathematician, much like a poet or painter, is a maker of patterns. To him, the abstract beauty of math was a canvas, allowing him to map the fundamental structures of our universe with both precision and artistry. In the late 1940s, the field of physics was divided by three competing frameworks for quantum electrodynamics: Richard Feynman's intuitive visual diagrams, Julian Schwinger's operator methods, and the work of Shinichiro Tomonaga. On a transformative 48-hour Greyhound bus ride in 1948, Freeman Dyson achieved a monumental breakthrough, realizing these seemingly conflicting theories were mathematically identical. By developing the Dyson series, he proved the theory was renormalizable, systematically removing the infinities that had long plagued the field. This unification resulted in the most precise agreement between theory and experiment in scientific history. Dyson's work didn't just solve a problem, it wove together disparate strands of genius into a single, elegant tapestry of physical law. In this slide, we explore the prime quantum connection, a bridge between two seemingly unrelated worlds. During a chance tea-time conversation with mathematician Hugh Montgomery at the Institute for Advanced Study, Dyson uncovered a startling harmony. The spacing of zeros in the Riemann zeta function aligns perfectly with the energy levels of heavy atomic nuclei. Guided by random matrix theory, this revelation showed that the distribution of prime numbers is governed by the same mathematical laws as complex physical systems. It is a testament to Dyson's unique ability to identify deep patterns, proving that the abstract language of number theory and the physical pulse of the universe speak with the same voice. Why doesn't the electromagnetic attraction between atomic nuclei and electrons cause matter to implode? In 1967, Freeman Dyson and Andrew Leonard answered this with the first rigorous mathematical proof of matter's stability. As depicted in The Stability of Matter, the mechanism is not simple electromagnetic repulsion, but the Pauli exclusion principle. This quantum law prevents fermions from occupying the same state, creating the macroscopic normal force that provides matter with its volume and solidity. Visualized as a protective shield within the atomic grid, this principle acts as the ultimate safeguard, ensuring the structural integrity of our physical world against subatomic collapse. As a terrestrial engineer, Freeman Dyson sought to harness the atom for both medicine and the stars. On the left is Triga, an inherently safe reactor designed for research and medical isotopes. Described as idiot-proof, it remains a global success today. Conversely, Project Orion represented an ambitious vision for deep space exploration to Mars and Saturn, powered by riding the shockwaves of controlled nuclear explosions. Though abandoned in 1965 due to the partial nuclear test-ban treaty, a cause Dyson himself supported, he fondly remembered this era of nuclear pulse propulsion as the happiest of his scientific life. This slide captures the dual nature of Dyson's terrestrial work, practical safety on Earth and daring curiosity toward the cosmos. In Deconstructing the Dyson Sphere, we separate science fiction from physical reality. The popular concept of a solid shell, inspired by Olaf Stapledon's Star Maker, is dismissed as mechanically impossible. Instead, Dyson envisioned a swarm, a loose biosphere of independent objects on individual orbits. This shift redefined the search for advanced civilizations. In The Hunt, Dyson suggested that rather than listening for radio signals, astronomers should look for the infrared waste heat emitted by these cosmic megastructures. By grounding the fantastic in the laws of thermodynamics, Dyson turned a dream of star-spanning energy into a practical method for exploring the universe's most ambitious possibilities. In the realm of biological astroengineering, Freeman Dyson proposes a future where biology and technology converge to conquer the void. We encounter the Dyson tree, a genetically engineered organism designed to take root on ice comets, utilizing starlight to create oxygen-filled habitats for humanity in the outer solar system. Alongside it stands the Astro Chicken, a revolutionary, 1-kilogram hybrid of biology and machinery. Inspired by von Neumann's automata, these self-replicating explorers are envisioned as a more efficient alternative to heavy, crude spacecraft. Together, these concepts reflect Dyson's vision of a cosmos cultivated like a garden, where life itself is the primary tool for exploration and expansion into the furthest reaches of our universe. In The Scientist as Rebel, we explore the rebellious ethos, a conviction that subversion is a creative necessity for truth seekers. This slide illustrates 4 pillars of defiance. First, anti-credentialism, a career that skipped the PhD to reach the heights of the Institute for Advanced Study. Next, historical revisionism that credits the Soviet invasion, rather than atomic bombs, for Japan's surrender. His climate skepticism prioritizes poverty over contested models, while his evolutionary ethics frame morality as a byproduct of natural selection. By chipping away at consensus like ice on a lake, this ethos demands we question established norms to ensure both intellectual growth and human progress. In Weapons, Hope, and the Human Soul, we witness the evolution of a scientist into a moral philosopher. As the disarmer, Dyson's first-hand experience with the tools of war led him to become a tireless advocate for arms control and the 1963 test-ban treaty. Embracing his role as the writer, he heeded the call to share his wisdom, earning acclaim for his poignant reflections on our collective future. Finally, as a Templeton laureate, Dyson bridged the divide between the laboratory and the cathedral. He viewed science and religion not as rivals, but as complementary windows into a single reality, insisting that our technological prowess must always be anchored in the service of social justice and human dignity. In the final analysis of a visionary life, we encounter the Maker's operating system. This intellectual engine runs on 3 interlocking pillars. First is rebellious independence, the refusal to be siloed by specialization or credentials, choosing instead to be a frog leaping between practical challenges. Next is mathematical rigor, which applies the elegant structures of pure number theory to the chaotic realities of engineering. Finally, profound humanism anchors every pursuit, demanding that technology serve as a tool for freedom and the narrowing of the gap between rich and poor. Together, these gears represent more than a methodology, they embody a conviction that the highest purpose of science is the flourishing of the human soul. We arrive at a final reflection titled Infinite in All Directions. This slide serves as a poignant tribute to Freeman J. Dyson, the eternal graduate student who dreamt among the stars. Robert Dakegraff, director of the Institute for Advanced Study, captures Dyson's essence by revealing his secret, a radical openness to life, simply saying yes to everything until the very end. Set against a backdrop of the cosmos and intricate technical blueprints, the image symbolizes a life that bridged the gap between mathematical precision and celestial wonder. Dyson's legacy is one of perpetual curiosity, inviting us to follow our own yes into the infinite patterns of the universe.